Hello everyone, my name is Xu Zheng. Today it's my pleasure to have this opportunity to present my work. My paper's title is An Effective Perturbation-Based Semi-Supervised Learning Method for Sound Event Detection. My presentation consists of 4 parts. Now let me begin. My research is on sound event detection, which is the task of determining both the category and occurrence time of a sound event. With the development of deep learning techniques, several mainstream deep neural networks have achieved the state-of-the-art SED performance. However, real-life SED is challenging because it is expensive and time-consuming to collect strong labels. A semi-supervised learning method can exploit weakly labeled data or unlabeled data to improve SED performance. Given this background, a task named large-scale weakly labeled semi-supervised sound event detection in domestic environments was conducted in the decades 2018 challenges. There are many types of semi-supervised learning methods, and MinTeacher has shown promising SED performance in decades challenges. In MinTeacher, two models have the same architecture, namely student and teacher. The teacher acts as an ensemble of the students to generate the targets for students, and consistency loss is employed as a regularization term. The key to effective MinTeacher is to choose suitable data perturbation to form a better teacher model from the student model, and thus improve target quality. Common approach of adding perturbation include Gaussian noise or dropout, and more effective data augmentation method can also be applied in SED tasks, such as back augmentation. In this paper, we focus on how to add effective perturbation for convolutional layers. Now, based on the motivation, let's talk about our method. Firstly, I'd like to introduce the MinTeacher-based framework for SED. The student model and teacher model are convolutional recurrent neural networks. The convolutional part is composed of 5 convolutional blocks, followed by 2 bi-GRU layers, and the consistency loss is defined as the expected distance between the AT output of teacher model and student model, presented in Figure A. The baseline core block is in the VGG style, which is composed of convolutional layer, batch normalization, and rectified linear units. And our proposed IC core block with time frequency channel attention module is shown in Figure B. The IC module is designed to generate perturbation to intermediate convolutional layer and statistics pooling-based time frequency channel attention module is proposed to improve the effectiveness of convolutional output. The detailed structure of our IC call block will be described as follows. In our paper, the IC module is designed as a combination of batch normalization and drop block operation. The batch normalization is applied to normalize the input to distribution with zero mean and unit variance. Compared to dropout, continuous regions of neurons are set to zero in drop block. So by randomly dropping neurons in this way, the IC module can effectively introduce the perturbation to the input of the convolutional layer. For output feature map, we introduce the statistics pooling-based time-frequency channel attention module, which means that different statistics information is used in the attention module. Given the feature map, there are two types of attention module, namely channel attention and time frequency attention. For channel attention module, we first use the statistics pooling to calculate the mean and standard deviation over the time frequency domain. And by concatenating the mean and STD, we get the channel representation Z. Then, after two fully collected layers, we get the channel attention feature map, and the output feature map is obtained by multiplying the channel attention feature map. For time frequency attention module, we first use the average pooling and max pooling over channel dimension. And then, after a convolutional layer, we get the time frequency attention map. The output feature map is obtained by multiplying the time frequency attention map. As for the arrangements of the channel attention and time frequency attention, the two attention modules can be arranged in the sequential or parallel manner. For sequential arrangement, which comes first also differs. If the channel attention is placed before the time frequency attention, we call this as CA plus TFA. By contrast, the TFA plus CA means that the TFA is placed before CA. Okay, we have shared the techniques. Now let's begin to show our results of experiments and analyze them. To begin with, I'd like to introduce the experiment setup. We use the weakly labeled and unlabeled in-domain dataset of the case 2018 and evaluate the performance on the evaluation dataset. And the log Meyer spectrograms are extracted with a window of 32 milliseconds. Specifically, there is a ramp-up for the learning rate over the first 20 epochs. An adaptive median filter is used for backend processing. The overall results is shown in the table. And from the results, we can see that the proposed IC module and the TFC-A module can achieve FE score over 39%. In addition, by combining the IC drop block and TFA plus CA module, the FE score can achieve around 39.8%, which significantly outperforms the previous winning score of 32.4%. Next, we evaluate the performance of dropout and drop block in the IC module. From the results, we can see that with the same drop probability, the performance of IC drop block is generally better than IC dropout. Indicating that our proposed IC drop block provides more effective perturbations for convolutional layers. Specifically, among different drop probabilities, IC drop block with probability equals to 0.05 has the best FE score. Finally, we also do some experiments on the different time frequency channel attention and different statistics information are used, such as mean, standard deviation, and max value. From the results, we can see that for channel attention, statistics pooling using mean and STD perform best, and TFA with mean and max value provides a slight improvement over the baseline system. And for arrangements of TFA and CA, the TFA plus CA sequential arrangement performs best. It achieves FE score of 39.5%. My presentation is coming to an end. Now I will conclude my work. In this paper, a new independent component module is proposed to introduce perturbations for different convolutional layers. The IC module is designed as a combination of batch normalization and drop block operations. Furthermore, the statistically pooling-based time frequency channel attention module is used to model interdependency between time frequency and channel domains. By combining the IC module and TFC-A module, the final FE score is 39.8%, outperforming the winning system's 32.4%. My presentation is finished. Thank you for your listening.